Hello, good morning, good day, good afternoon, good evening, good night, wherever you are in the world again. And welcome to another stream here for Freaky Physics. We have CJ today. Again, we're doing a lot of paper practice. This time we're doing paper three. We finished a paper three question last time, but so that means we're gonna go through another one soon. Okay. Um, all right, so he's not in yet. I'm gonna just join anyway. Um, I'm gonna see if he's aware that there should be a lesson, but if not, well, it's because I moved the lesson from yesterday. It's supposed to be yesterday, but I was traveling. For some of you may be aware of that. So we were traveling. We just came back home yesterday, and I wasn't able to make it on time. So, but anyway, he should be aware that we're in for today. I'll just wait for him for a while. In the meantime, I'm going to open the past papers that we have used. Hmm. Hmm. Okay. It's not in yet. So I'm gonna ask if he has remembered today's lesson. If not, we're okay to either move it. If he's not ready, we'll just move it to Friday because this is not our normal lesson days. So better. I'm just gonna go ask him right now. Okay. Hold on. Give me a sec here. All right. So while we're waiting for that, okay, I'll just get ready with some past papers here. Okay, we'll use those. Mm-hmm. All right, here. Okay, there he is. So let's wait for him to get in. Hi, CJ. Sorry, say that again, please. No, it was like, hold on. Hear me now properly?
Did your microphone unplug?
Yeah, I think. No,
Because I
uh,
heard you like for a bit.
yeah, I unplugged it for a while because the sound was coming out of my speakers instead of the headphones. All right. So how hot is
Hello?
it here? Hold on, this is weird. How come you cannot hear me? Hold on, let me check settings. All right, can you hear me now?
Hello?
Hello, can you hear me now?
Yes.
Okay. All right, now. Okay, so anyway, how hot? I haven't checked. I haven't actually checked myself, but I looked at my phone. Was around 33 degrees today.
That's hot.
Yeah. How about there? How hot was it over there?
My Indonesian friend, they sent me something. It
Mm-hmm.
was like about my school,
Uh-huh.
like how it's trending on Facebook.
Oh.
Because there's like a baseball, like there's like a track and field and baseball like
Mm-hmm.
tournament
Right.
in 36 degrees, but it said it feels like 47 somehow.
Oh, feels like 47. Must be the humidity.
Yeah,
Okay.
it's very humid. I think it's very humid there as well.
Yeah, it is, especially near the coast. But we did go to the beach. When we went to the beach, it wasn't that hot. So I guess it's mostly in the cities at the moment.
Hmm.
Okay.
Oh, it just rained today,
Ah, that's
luckily,
well, that's good to hear.
but still really hot. Oh, never mind. It says 38, but feels like 47.
Uh-huh.
And this is at my school. Like they found my school just
Right.
from Facebook.
Uh-huh. I, I
Yeah.
just gotta wonder how everybody was able to play.
No, they took lots of breaks.
Right.
And it was windy. It was windy.
Okay, wind would help. Definitely would help there. All right. So anyway, so we're continuing with paper three. All right. Let me just.
Hmm.
Did we finish 2016 already? Let me just check. May 2016. Uh, let's get. Let me just look. Okay. Okay. I'm just checking if we've done everything. That's no. Astrophysics. Okay, that's done. Okay, we haven't finished it yet, so I'll be opening the 2016 paper first, and then we'll start. Yeah.
Hmm.
Okay. Okay. Same as before. We're still using the same. Uh, excuse me. We're still using the same link for the board. Okay.
Hmm. I want to say that when you leave the board, like I can't open the link.
Oh. Okay. So that I guess that means I better just stay. That board just stays online. It's okay. I can keep it like that. No worries.
Oh, can?
Yeah. I just won't have to close it here. That's all I have to do.
Mm.
Okay. Um, that was physics, SL paper three. All right. Let me just share my board now as well. Okay. All right. So let's get this on, and that should work right there. Okay. Um. Okay. So here's the next question we're gonna do today. That's done. That's done. Astrophysics nebula. Okay. Question. Okay. So we were just finished with question 12. Now we're gonna do
Mm.
question 13. Okay. Um, for this question, you're given a star. This particular kind of question will always be given. You're gonna be given a star and some properties of that star. Okay.
Mm.
Um. Okay. There we go. Okay. So in this case, that's our question. So we have Aldebaran It's a red giant star with a peak wavelength of 740 nanometers and a mass of 1.7 solar masses. What you have to do here in the first part is to show that the surface temperature of Aldebaran is around 4,000 kelvins. Okay. Let me just
Mhm.
open the data booklet for relevant formulas. Okay. This time I'm going to just copy all three. Okay. So for astrophysics, these are the formulas you need. And I'll just put them here for now. Okay. Any idea how to solve these? Um, Again, you're given the peak wavelength and the mass. First is you need to show the surface temperature to be around 4,000 kelvins.
So the D2 first equation.
Mm-hmm. D2 first equation is correct. All right. So you,
So we do um oh oh do I divide, yeah.
mm-hmm.
2.9 times 10 to the negative 3 divided by 740 nanometers, which is 10 to the negative 6. I don't know.
Okay. Right.
I'm making it.
Nanometers, not 10 to the 6. Nano is 10 to the minus 9.
Okay.
All right. But anyway, you can check that later on in the data booklet if you want to see the prefixes, right? But for now, I'll help you with the prefix. So this is 10 to the minus 9.
Mm-hmm.
Okay. So yeah, you're right. So you're going to use that formula. So that's going to be lambda max
Yeah,
T
and I see
equals.
because it's written in
Mm-hmm.
two significant figures,
Uh-huh.
my answer will be um 3900.
Okay. So correct. So in this case, temperature will be equal to that, as you said, times 10 to the minus 3 meters Kelvin. And then you're dividing this by 740 times 10 to the minus 9. Correct. Then your temperature, you're going to get that as 3,900 Kelvin to 2 sig figs, which
Mm,
is the correct way to do it. Once you get this, you have to write now this part that it's approximately 4,000 Kelvin. Okay?
mm,
All right. So if you're again, this part is for the instruction show.
mm-hmm.
Okay? All right, so great. Let's go to the second question. You're given the radius this time. So again, very common question. You're just usually given some information on the star again. So this is another example of that. So the radius is given. Determine the luminosity of Aldebaran. Aldebaran. I don't know how to pronounce that properly.
I don't even know what it is.
Okay, it's one of the stars. I can't remember where it is, but it's one of the stars in the more um famous constellations.
Mhm.
Okay. So going back to the formula booklet,
Oh, it's D1 second equation.
D1 second equation, correct. Okay.
So we change it to pi r squared.
Correct. No, sorry, not pi r squared.
4 pi r squared.
It should be 4 pi r squared because we're dealing with a sphere, not a circle.
Oh, okay.
Okay.
Okay, I got it.
Okay. All right. So again, so we're
What's
gonna
Stefan
use.
Boltzmann times 10 to the negative
Okay. Hold on. Let me
9,
get the data booklet on that.
8, 9?
Uh,
I don't know.
5678.
Okay.
5.678.
Mm-hmm.
5.67 10 to the minus 8 there. Okay.
Mm-hmm.
Okay, but anyway, Stefan Boltzmann constant. Let me just put that here for your reference. Oh, okay. Okay. If I'm gonna follow the American pronunciation, it's Aldebaran.
Aldebaran?
Yeah. If I'm gonna,
Well, British.
it's slightly different. In the It's gonna be Aldebaran.
Aldebaran.
I
Al-
actually, for once, I find the American pronunciation easier on this one.
yeah, because there's less syllables
Yeah,
and kind of less tongue twisty.
yeah,
I got
Aldebaran.
2.7
Two
times
points.
10 to the 18.
Okay, so let's just do that quick. So this is correct. So you're gonna use second equation as you said, luminosity equals sigma A t to the 4. Then you're just gonna put your values in 5.67 times 10 to the minus 8. The area, as you said, is 4 pi times r is 3.1 times 10 to the 10 squared. Then the t to the 4, you're gonna use 4,000 to the 4. Okay.
Mhm.
All right. So if you put that in the calculator, I'm gonna just check the mark scheme here to the which one is it? All right. So the correct answer here is 1.8 times 10 to the 29. All right. So let me just write the correct answer again. This is 1.8 times 10 to the 29. So, yeah,
Oh,
29 watts. Okay. So you
oh,
had a slightly
oh!
different answer.
I used my answer.
Okay. You used your 39,000, right? Um,
Yeah, I used
okay.
3918.9.
That's
I used
fine.
all the decimal places.
That's fine. That's fine. Um, as long as you use one of those numbers, it should be fine. Okay. So if you use 4,000, then this is the answer. If you use 3,900, then you should get 1.6. Okay.
Oh, for some reason I
So
didn't.
double check that. So if if T equals 3,900
Oh, to the
Kelvin,
four. It's
yeah,
T to the four.
yeah, don't forget this to the 4. Okay.
Yeah, I got 1.6 then.
1.6 times 10 to the 29 watts. Okay. All right. Okay, where's the question? Okay. So this next question, it's a little bit related to quantum mechanics. Again, this is again another common question that comes up. Okay, so here, so you have to outline, or basically you have to give us a short account on how the light of Aldebaran gives evidence to its composition. How do you, basically the question here is, we know that this star is gonna be made of either hydrogen or primarily hydrogen or primarily helium. The question here is, how do we know which one is which?
Oh. Hmm. Oh. Um. How much light?
Mm-hmm.
Wait. Composition? What does that
Right.
mean?
Okay. Composition here means what is it made up of mostly? Is it, for example, at this point, it doesn't matter what it's made of, but let's just say for argument's sake, let's say that this is a main sequence star. So how do we
Hmm.
know its main sequence? We know its main sequence because it's mostly hydrogen. How do we know it's mostly hydrogen? No,
Because it's burning
similarly,
or something.
yeah. But similarly, if it's already a red giant, then it's mostly helium. Then how do we know it's mostly helium?
Because it's a red giant.
Uh-huh. Actually, it's the other way around. It's not because it's a red giant. Okay. Now, okay, so I guess I'll just explain this to you how this is done. Yeah. So whenever you see the word composition, always think absorption spectrum. Okay. Because what do we know about the absorption spectrum? Back in not in astrophysics but in quantum mechanics, we know that each element due to its um, electron structure, right?
Hmm.
Structure will absorb different wavelengths of light. Now, specifically, hydrogen will always absorb a certain set of wavelengths. Helium will absorb a different set, and so on, as long as they're a gas. Okay, will absorb different wavelengths. So I'm just gonna show you exactly what I mean by that. If we actually look for the absorption spectrum of different gases, I'm just gonna compare hydrogen and helium. Uh, okay, hydrogen's absorption spectrum kinda looks like this. Okay, so hold on. So this is what helium looks like. And I'm gonna try to get, sorry, that's hydrogen. Okay. And which one is helium here? Absorption. This one's gonna be helium. I'm just gonna again copy and paste this right here. So again, this is hydrogen. I'll just move this here first and make this. Okay. So this is hydrogen. This is helium. You see that the lines are different. The absorption lines are different. So if we look at the light of any star and we look for these absorption spectra, we will see what the composition is. All right.
Mhm.
So these are different frequencies absorbed, right? Okay. So this is the idea on how to determine its composition. You, if it's a combination, if it's some sort of combination, then what do we get? Let me see. I think I have something. Oh, okay. I think this is even better. But anyway, hydrogen combined. Okay. Let's see if I can find something that combines it. Yeah, this is what it looks like if it's combined. And I'm gonna get this particular bit in. Okay.
Mhm.
Okay. Hold on. There we go. So this is what it looks like once it's combined. So you see it's the line, the absorption lines are kind of like when you put those two together, right? So this particular line comes from the hydrogen, which is this, and then this particular line comes from this, the helium line. And this line here comes from this line here from helium. Okay. All right. So so that's the longer way to say it, but there's a shorter way to say this now that we're aware of what to do. Right? So going
Mhm.
back to the question, uh okay. So outline how the light from Aldebaran gives evidence to its composition. Okay. Question
It
now.
depends on the temperature.
No, it doesn't.
Oh.
Emitted also doesn't really depend on temperature. What the emitted light will have a different color, but the spectrum will remain the same. It's just that the intensity is going to be brighter somewhere else. Okay. All right. What matters here is that this is only the composition of the um thing. So
Absorptions.
I'm just going to write the answer here. The best possible answer here is um each element. So I'm going to write it like this. Each element in the stars composition, right, will
Mhm.
absorb specific wavelengths of light or frequencies. I'm going to use frequencies in this case. Specific frequencies of light, right? And then which show up as absorption, which show up as absorption spectra, which show up as a particular pattern uh, as a particular pattern of an absorption spectrum. So I'm gonna write it like this, and I think this is gonna get 2 marks.
Mm.
Absorption spectrum. Okay.
Uh-huh.
Okay, so this is the best possible answer here. Okay, now I'm now looking at the marking scheme, and it's exactly the same thing. So yeah, we get 2 marks.
Each
Let's.
element distorts composition.
Mm-hmm.
Yeah. So okay, all elements are present, but it depends on how much of it there is.
Yep. Yep. So
So
think
what?
about it this way. If there's a lot more hydrogen and there's a significant amount of helium, you would see this, right? You would
Mhm.
see uh yeah, you'll see this thing, right? But imagine that there's a significant amount of carbon again. If there's a significant amount of carbon, then there are going to be more absorption lines, which match carbon's absorption lines.
Mhm.
Right now, there is carbon, but it's insignificant at this point, so there's no effect on the spectrum. Right? Okay. All right, is that clear?
Yeah.
All right, let's go to the next question. This one's pretty easy. It's 1 mark. Okay. So identify the element that is fusing at Aldebaran's core at this stage. Now remember, if we go back to the start of the question, let's just go back to the start of the question. It says that Aldebaran is a red giant,
Hmm.
right? So is it hydrogen or helium? Or is it something else?
Helium.
It should be helium. Okay.
Mhm.
So because it's just identify, it's just helium. But let's write down the complete answer. It's helium because it's a red giant, right?
Mhm.
Okay, great. Next question. Uh, predict the likely future evolution of Aldebaran. That's the last question on this part. Okay.
Mhm.
Let me do that again. Okay. So again, identify or predict rather the likely future evolution of Aldebaran. So basically, from red giant, it's just gonna ask you, is it gonna go to neutron star or black hole or white dwarf? That's
Not white dwarf
uh why not? Okay, I think I'll put the introductory part here again. Uh
because um. Wait, does it become a white dwarf? I thought Earth becomes a white dwarf.
not really.
Oh, really? Then
It's
what becomes a white dwarf?
stars become white dwarfs.
All of them?
But yeah, all not all of them. Some of them do.
I thought they turn into like black holes.
No, there's a certain condition. Try to remember that condition. Okay. Oh,
When
by the way,
everything
this
is.
is 3 marks, right? So this is 3 marks. So that's only gonna be 1 mark.
Hmm.
Okay.
Okay, so when they burn up all the helium.
Mm-hmm.
Oh, there was a word.
Yes.
Um, does it connect to neutron?
Not quite yet.
Oh, not that word.
No.
I don't know it.
Okay. Let's go back to the story. We all remember there's always a story on how stars evolve. It's basically all the same, right? So you
Hmm.
have at the beginning, you have your nebula, right? And then your nebula breaks up into smaller bits of approximately 1 solar mass. Okay. And then what happens is it turns into I'll just write it in words, main sequence. Then from main sequence, it always goes to red giant, right?
Hmm.
And then what happens afterwards is it's going to, I'm just going to use the word explode first because there are 2 types of explosions here,
Hmm.
right? And then what happens afterwards depends on the remnant. So large remnant, medium-sized remnant, or small remnant, right? If it's a large remnant, it's going to be a black hole. If it's a medium-sized remnant, it's going to be a neutron star. And if it's a tiny remnant or a small remnant, then it's going to become a white dwarf.
What is remnant meant in
Okay,
this case?
now think about it this way, because the star explodes, a
There are
lot of
pieces
them,
that
there are
like
pieces that are yeah, go ahead. You were saying something. I think you're onto
right,
something here.
like by remnant, do you mean like the exact definition, like small pieces that turn into something else?
Yes, but in this particular case, we want to make sure that this remnant is something in particular. It's the core of the star. Okay, so the
Mhm.
remnants are so core remnant. Okay, so it's a core remnant like there. So when the star explodes, the core remains. The rest of it goes out. Yeah. So
Mhm.
okay, so it's the same story over and over again. It's just the difference now is one, the mass that you start with, and two, the mass that you end up with. Okay, so basically we're gonna okay, so we're before we go there, we're gonna add this now. So what exactly happens? So if the red giant, okay, once it explodes, there are two possible explosions it can go through. Okay, the first type is just a planetary nebula, nebula,
Mhm.
and the second one is a supernova. Okay, supernova. To be specific, type 2, Roman numeral 2, like that. Okay, now when you have a planetary nebula, what happens? The remnant, usually the mass is equal is less than or equal to 1.44 solar masses, or let's just use 1.4 solar masses. Okay, and then what happens here, this core remnant it's gonna turn into the white dwarf.
Mhm.
Okay, so that's the first part, right? Now if you have a type 2 supernova, what happens is your core remnant, let's just move that a bit here, the mass can have two possible values. The mass could be between 1.4 and most say 3. So I'm going to use 3 solar masses. Okay, and then we have the possibility of that mass being greater than 3 solar masses. Okay, now
Mhm.
these numbers, this is going, by the way, this is going to give you the neutron star. And then the last bit here, greater than 3 solar masses, this is the black hole. Okay, right. Now,
Mhm.
so let's just name the last bit here before we continue. So if we look here, this value and this value, they have names. Okay, so this is a Chandrasekhar limit. I think you
All right.
remember that,
Yeah.
right? So this is a Chandrasekhar limit. Okay, and this is the TOV limit. The I forgot the T again. The Oppenheimer-Volkov limit.
I don't know that one.
Yeah. You usually are not taught this because this is in HL. This particular limit. This is in HL. However, all you have to remember between the two is the Chandrasekhar limit. Okay.
Mhm.
So you don't really need to remember this particular limit. No need to memorize. Okay. However,
Okay.
this must be memorized, the Chandrasekhar limit. Okay. All right, so going back, so how would you get your 3 marks? Just go to this bit. So you're at the red giant, just go to this bit. So what's the first step? The red giant.
Oh, red giant explosion, and
Uh-huh.
then a remnant becomes either um
Okay.
black hole if certain conditions meet,
Uh-huh.
or white dwarf if
Uh-huh.
like it can't burn anymore.
Okay, I'm gonna give you one clue here. Here it says that the star itself is 1.7 solar masses. So
Mm-hmm.
imagine this. The star explodes. What's gonna be more likely? It's gonna, of course, it's gonna lose mass from that explosion, right?
Mm-hmm.
But what's gonna be more likely scenario? It keeps a lot of that mass. It stays close to 1.7, or it loses a lot of mass, and then it goes below the Chandrasekhar limit. What's the more likely scenario here? Given
It
that the
goes
mass is
below.
1.7, it goes below. So you go that more likely route. So
Mm-hmm.
go back here. What kind of explosion do we expect to see? Planetary nebula or supernova?
Supernova, because planetary nebula, doesn't that create something?
Yeah, they both create something. A
Oh.
planetary nebula, oops, sorry. A planetary nebula is basically just a star exploding, but it's not powerful enough to send stuff across the universe like a supernova would.
Mhm. So what
Okay.
does it do?
Okay.
Does it make like a solar system? Like
Oh,
what?
I think I better just show you an image of a planetary nebula versus
Mhm.
supernova. Okay.
Mhm.
Okay. So while I'm looking for a good image here, what? Let's continue. You continue your answer first here. Versus.
Um, so the light from the
Mm-hmm.
Aldebaran gives
Aldebaran.
evidence
Yep.
its Aldebaran gives evidence of its composition. Wait, that's not what we're doing.
Mm-hmm.
Um, the future is that okay, so ex- it will what's it called? Become a red giant.
It's already a red giant.
It's a red
Remember?
giant, so it will
Yep.
explode. Since it's already a red giant, it will um
But which explosion are we gonna need here? Planetary nebula or supernova? The more likely one.
supernova.
Remember, okay, here's the deal. You look at the remnant. You don't look at the star itself. You look at the remnant. If the
Mm-hmm.
remnant is gonna be small, it's gonna be mostly a planetary nebula. If the remnant's gonna be large, it's most likely to be a supernova.
Isn't 1.7 solar masses almost double like
Yeah, but this
even
1.7 is the star itself. It's not gonna be the remnant, right?
mm-hmm.
Okay, so it's not just gonna be the core. Okay, so the best explosion that you need to go through here is the planetary nebula.
Mm-hmm.
Okay, because again of the relatively small mass of Aldebaran. Aldebaran here's 1.7 solar masses. It can't go supernova. Sorry, it can't go into black hole. It's too small, right?
Mm-hmm.
And then because it's got a shed mass rather. Um, this means that the explosion will be powerful enough to send pieces of it out of the thing, out of the star, but not powerful enough to totally destroy the star. In other words, um, you, okay, here's something that would be likely. The core would contain about 50% of the, yeah, about 50% of the mass of the star. Again, the core would contain about 50% of the mass of the star, at least. And at most, I'm not sure, but let's keep it at 50 for now. Okay. So think about it this way. If the core is going to get 50% of the mass of the sun, or of that star, that's 1.7. That's going to be approximately zero point 0.8 or zero point 0.9 solar masses left over, right?
Mm-hmm.
Okay. So the idea now is once it explodes, the core remnant will have a mass less than the Chandrasekhar limit. So this tells
Mm-hmm.
us that we're going to get a white dwarf, and therefore the explosion must be planetary nebula. Okay. So I'm gonna go through the logic first, the logic of thinking to make it easier for you to write this, and then you write it in the correct order. The logic
Mm.
is, again, the logic is it's got a small mass. So once the explosion's done, it must have a small mass. The remnant must have a small mass. And a small mass would lead to a white dwarf. And therefore, if you have a white dwarf, the explosion can only be a planetary nebula. So that's the way you
White
think it.
dwarfs can explode.
No, the star, the white dwarf itself doesn't explode. It's the result.
Oh, okay.
So okay, let me write
Okay.
that down again
Wait,
further.
how big does it have to be a supernova? How many solar
The
masses?
star itself or the remnant?
The star.
The star itself, well, it really depends on the conditions of the star, but the supernova tends to be at least 10 solar masses to start with.
Okay.
Okay, so that's one thing that would be easier to remember, I guess. Yeah, I'll just put it here. So, uh, so I'm just gonna say small stars have a mass less than 10 solar masses. And this would result in a remnant whose mass is gonna be less than 3 solar masses, definitely. Okay. All right. So there. So that's why some small stars would become could still become neutron stars, but most small stars would be like go into white dwarf phase. Okay.
Mm.
All right. So again, let's write the final answer here before we continue. So it's going to be our final answer here.
The red giant
Okay.
um explodes.
Okay, I'm going to word
Oh,
okay, just going to put the word explodes here. We're going to change that later.
through a planetary. Oh wait, nebula. Wait,
Yeah. Yeah.
explodes planetary The
Okay.
explosion is a planetary nebula.
Okay, or you can say creating a planetary nebula, right?
Oh, yeah. The red giant the red giant creates a planetary nebula,
Okay.
which
Okay.
then wait, I think I
Okay.
worded it wrong.
This is actually okay, go ahead. How would you say it first? Then we'll correct whatever
The red
needs to be.
giant explodes, creating a planetary nebula,
Mhm.
and its remnant, since it is no, I'm gonna be realistic. I'm not gonna
Okay.
say Chandrasekhar limit. Do I say Chandrasekhar
You can
limit?
say it. You can say it. Or
Um,
you can say either that or the actual value. So okay, you said the remnant. I'm gonna put core here just to make sure that you say it correctly. You have to put the word core here. Okay, the core
okay.
remnant has or will have what, a mass. Okay, you said Chandrasekhar limit, is that gonna be less than, equal to, or greater than?
Less than 1.4 solar masses.
Okay, so less than 1.4 solar masses. So what happens?
Um, Resulting in a white dwarf.
Okay, resulting in a white dwarf. Okay, this is already 3 marks according to the marking scheme. Okay. There are other things here in the marking scheme. I'm
What
going
is this?
Okay, I'm gonna change this word explodes. There is a specific term for this thing. This is called the helium flash.
Oh my!
Yes, it's a
I
very
would not
technical term, so I don't expect you to try to memorize this. Yeah.
know. Mhm.
Okay. If you use the term helium flash, though, this would this would definitely be 3 marks because this is hitting a fourth mark already. Okay. All right, the helium, and then what happens because of that helium flash? Of course, it's a flash. That means the outer shell or the outer layers of the star will expand, right?
Hmm.
So outer layers expand. Okay. So the helium, because of the helium flash, the outer layer expands, and that's what the planetary nebula is. Okay. So the explosion is this bit: helium flash, then the outer layers expand. That's it. Done. Okay.
Hmm.
All right. I hope this is clear. So let's move
No.
on. Okay. Let's move on to um the next question. Let's see. Okay. This is the last page. I think I can just copy and paste all the questions at once. Okay. Okay. So this time we're looking at the quasar. A quasar is just a very bright object in deep space. Okay. So deep space means it's really far away from us. Okay.
Hmm.
So at this point, it doesn't matter what we're looking at. The important thing is we're looking at something and it's got a z factor right here. So what is z? I think you can get this from the data booklet.
Is that the redshift?
It is the redshift.
Oh, so I just say redshift.
Yeah, done. Okay, hold on. I'll just copy the data booklet stuff here. This is the relevant portion for from the data booklet. Okay.
Do I just put the equation or do I just put z means redshift?
No, because it says here you should outline what it means, right? So what
Yeah.
is redshift? That's the question here. So you're right that it is redshift, but you have to state what exactly is redshift.
Oh, oh, oh. Oh, there's blue shift and redshift. Oh, redshift means it's moving towards the Earth. It's
Uh,
moving quicker towards the Earth.
hmm.
Or is it the further it is, the faster it goes?
Okay. Let
Or
me
is it
think.
something about like the growth? Like, no, it's not.
Okay. I'm gonna give you a clue here. You said redshift, right? Z itself is not the redshift.
Is it R that's redshift?
No, redshift is, I'll just say it here. Redshift is actually equal to delta lambda, the change in the wavelength. That's the redshift. However, Z, as you see, whoops, go back. Okay, so, okay, I'll make it smaller first so it's easier to scroll through. Okay, here we go. And then let's zoom back out. Okay. So again, when you say redshift, you don't necessarily, Z is not the redshift. Z is a measure of the redshift.
Hmm.
Okay. Now, how would I say it myself? Z, I'm just gonna, since I see something here in the formula booklet, that's what I'm gonna write. Lambda over lambda, right? Lambda 0, right? But what
Hmm.
is that? I have to explain this. This is the redshift. Okay. So this part is the redshift, and what's lambda 0? That's the wavelength, original wavelength of light. So it's a ratio, no redshift, right?
Hmm.
Okay. So okay, so let me discuss this briefly before we move on. So what do we what, for example, let's say here, let's say that the original wavelength is let's give it a 600 nanometers, and then the new wavelength is 605 nanometers. So the redshift would be equal to 5 nanometers.
Mm-hmm.
Okay. And then Z would be equal to 5 nanometers over 600 nanometers. Okay. Okay. So, yeah, basically that's it. In other words, yeah, the reason why redshift here is not enough is because the word redshift, you need to kind of explain what that is.
Mm-hmm.
Either way, okay. So just be careful here. If it seems like it's just a one-word answer, it normally never is one.
Mm-hmm.
All right. So this is a good answer already, but again, you have to say the words. You don't leave it as symbols. Okay. Now,
Mm-hmm.
I could one last thing. I could further say this as change in wavelength over or no original wavelength, right? Okay. Now, this is the best thing you can answer with, but you can also say you can actually say that this is a measure of the cosmological, not just any redshift, but you have to say cosmological here.
Mm-hmm.
Redshift, okay? Now, in all honesty, I find the first possible answer easier because you have a formula, you just need to explain it. All right? Okay. Now, let's take a look here at the second question. Calculate the ratio of the size of the universe when the light was emitted by the quasar to the present size of the universe. So so you're comparing two sizes, right? So which one of these from the formulas is the best possible thing to do? Thing to use here.
Size of the universe. Um, is it not the R? Wait, no, 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 no. Hubble. Hubble.
Not quite Hubble.
Not
I'll give you
Hubble.
a clue. You have Z. You have Z.
Oh, so it's R over R O
Mm-hmm.
minus one.
Okay, this is it. Okay. Okay. So you use that. Now the question is, I'll give you a clue. You could possibly interchange the values for R and RO. There's a possibility doing that, right?
Mm-hmm.
But I'll give you a clue here.
Oh, one of them is one.
Un- Not necessarily,
Oh,
but
okay.
yes, they can. One of them can be one, and one could be the 0 point whatever the value is, right?
Mm-hmm.
However, I'm going to give you a clue here. All right. Remember that the universe is expanding. So it must
Yeah.
have been smaller in the past. So once you
Mm-hmm.
get two possible answers, you need to make sure that you use the correct value. It must be smaller in the past compared to now. Okay.
Mm-hmm.
All right. So with that, calculate.
So if it's smaller in the past, wouldn't like Z be like zero?
No, not necessary. Your Z is
Not.
given.
What's R mean again?
R is the okay. In this case, both R's mean size of the universe. Okay.
Okay, so if the universe started from like the smallest it could be,
Mm-hmm.
could that just be zero or no?
At if you're talking about the absolute beginning of the universe, yes, that can be zero. But you never get to those kinds of problems.
Oh.
Okay. All right. So here's the thing. Just use the formula first. And I'm going to tell you, you don't have to find the value of R or R0. You just need to keep the ratio because that is the question itself. You're looking for the ratio, right?
Mm-hmm.
Okay.
Ratio. Can I just write R over RO?
Mm-hmm. So what's that going to be? R over RO will be equal to,
Um, one.
no, not 1.
Um, uh, um, is it a fraction or is it just a digit, an
Did
integer?
Okay, I'll give you a clue. You just look for it. You don't really need to find the value of r over ro straight away. You're gonna use the fact that you have a z given to you.
Z is given.
Yeah.
Oh wait, sorry. You can see it.
Oh, okay. Let me put that down. So you should. Okay. Z is given right here.
Okay.
Okay.
Since Z is 1.6, 0.16.
What's r over r? Oh,
Oh, 16 over 100.
ah,
No, no,
no,
no.
no, but close.
Um, Something minus one. Why is the minus one there?
There's a minus one here. Correct. So let's put that in there. Minus one equals z, right? But you're given a z,
Oh, then 0.16.
0.16. Correct. So what do you get with r over r0?
Oh my. Can we multiply it by 6?
Don't just move
Can we plus
this.
the 1?
Yeah, just
Yeah.
add one, right? So r over r0 will be what?
1.16.
1.16. Okay, this is telling you something. This is bigger than 1. So this is not the answer, right?
Yeah. Oh, I remember before you were like, it's you should do plus 1 instead.
No, actually, this is correct. This is correct. However, you did the plus 1 already, right?
Oh,
Okay,
yeah.
here's the deal. This is already a ratio, but it's a big number. So which one do you expect R to be? Is this the current or the past? Is this the
Current,
present? This is present, right?
present.
And then this is past, right?
Yes.
That's the only way you get a that's the only way you get a number bigger than 1. But the question is not about present to past. The question is past to present.
So we flip it
You flip it over,
and
correct.
put 1 over 1.16.
Okay, r0 over r is equal to 1 over 1.16, which, of course, this being physics, we're not happy with the fraction. We
Oh,
change that to a decimal.
which is 0.86.
0.86. There. That gives you your 1 mark, and that's a correct answer.
Mm-hmm.
Okay. Now, so just think of it like that. The present's always bigger than the past in terms of the size of the universe. And then that's what you use to figure out which of those R's is the present and which one's the past. RO is
Mm-hmm.
usually the one in the past. Yeah.
Mm-hmm.
All right. Uh, well, we're gonna be a bit over time right now, but do you wanna just keep going until we finish this set of problems?
Sure.
All right. All right. Calculate the distance. Okay. Calculate part three is rather easy, I guess. You're given. Okay. Okay. This is 2 marks, I guess. So that means you need one or two equations. Okay. Remember that I'll put that thing in. That's gonna be useful. Zero z equals 0.16. That's gonna be useful.
Mm-hmm.
Okay. Which equation or equations do you need to use here?
The distance. So the V equals Hubble D.
Okay, we need this one here. So we'll put that V equals Hubble constant times D. That's 1. You need another one.
Okay, the other Hubble.
No, you
No,
don't need the other Hubble yet.
the is it
I'll give you.
given here?
Yeah, it's given. It's the first one.
Oh, okay. Oh,
Wha-
V over C.
Z equals V over C, right?
Yeah.
Okay. So since we're looking for the distance, remember the clue. I remember the test technique I've taught you before.
Z equals HD over C.
Ah, so this is gonna be H0 D over C. Correct. right? So
Mhm.
so let's just that put that in there, right? So what now? Since you're looking for the distance, you just rearrange that, right? So
Uh,
from here, rearrange that. D equals, well, I'll do that now. dz over h0, right? Okay, and then put the
mhm.
values in and find the value of d. Now, in this case, you're okay to leave this in megaparsecs because we are talking about huge
Oh, oh, oh,
distances.
yeah. Okay. Um, I got it.
What's your
It's
answer?
uh um um 3800.
3800? No, not quite.
3800.
D 3800? No, that's too small.
Wait, really? Wait, I used 0.8. I used the answer previously.
Um, no, that remember the previous answer is not z. The previous answer is the ratio of the sizes.
Oh yeah, it is. Okay, 0.16 then?
Mm-hmm. And then C is, I think we agree what C is. That's going to be 3 times 10 to the 8. And then
Yes.
H0 is given 68. Um, but this is in meters per second, right?
Mm-hmm.
Okay. This is in 68. Then we have to do 1,000 kilometers per second per megaparsec, right? So basically, oh, this becomes meters per second now, right? So that meters per second here cancels out. Then you get the final answer. So in this case, you have to be careful. Convert that 68 kilometers per second into meters per second.
I did, and I got 706.
706, correct.
Oh,
Done. Yeah, that's correct. Okay, you can leave it at megaparsecs. Don't need to convert to meters. Okay,
mm-hmm.
all right. Last one, cosmic microwave background radiation.
Oh, because uh is distributed equally across the universe,
Mm-hmm.
it shows that the universe expands.
Mm-hmm. Uh, Hold on. Let me see the mark scheme here real quick. Uh, not it's not the that's not the reason. You just said it's even or it's uniform across the universe, right? That's true,
Yeah.
but that's not the reason that supports hot Big Bang. The hot Big Bang. It supports the idea that there was a Big Bang,
Oh
okay?
yeah.
But the hot part, we need to support it with something else. Okay? But you okay. Okay, I'm just gonna write it now here. Okay. So here is the hot Big Bang, right? Emphasis
Mm-hmm.
on hot. Okay. And then here I'm gonna put hot Big Bang here as well, but emphasis on Big Bang. Okay. Okay. The best feature here for the cosmic microwave background radiation is that the wavelength corresponds to an expanded corresponds to temperature of universe, right?
Mm-hmm.
Okay, and then what happens is due to expansion, uh, this means that in the past, okay, in past, the universe was hot. The wavelength was shorter, right?
Yes.
And thus, the universe is hotter, and thus, universe was hotter. Okay,
Mhm.
Was hotter. Okay, so this is the part that supports the hot part of the hot Big Bang theory. For the other one, for supporting the part about Big Bang, okay, this means what you do here is the wavelength is uniform across the universe, right? That's the one you're
Mhm.
saying. Uniform across the universe. So that means in the past, the what's this? The radiation must have been must have been um produced at produced all at once in a small area. In a small area or small space. Okay.
Mhm.
All right. So that's the slight difference in how to approach these two problems. If the okay, let me just see the mark scheme itself, see which one it is. Okay. So in this case it's not clear which one are we in the question itself. It's not clear whether we're talking about the hot part or the Big Bang part, right?
Mhm.
So it would be a good idea to say these two at the moment. Okay. Now, looking at the marking scheme though, it is referring to hot, the hot
Wait, when
section.
you say corresponds, do you mean like proportional?
I don't know. What I mean here is the marking scheme says
Oh
the
no,
mar-
sorry. I meant for the answer.
okay. So in this case, again, the word hot here would mean this is the answer. And then if you focus on the term Big Bang, then this is the answer here. But you need
Mhm.
both to actually explain the whole hot Big Bang theory.
Um,
You need both of
Also,
these. Okay.
does correspond mean proportional to?
Oh, hold on. Which part are we talking about?
Wavelength corresponds to temperature of universe.
Oh, yes, yes. Yeah.
So wavelength proportional to temperature of universe.
Uh-huh. Yeah.
Okay.
Proportional. And then the other part here is let's just do the present. Presently, this the temperature is what is it? 3 Kelvin? Approximately 3 Kelvin. Yeah. Okay.
Hmm.
Presently, the temperature of this means the wavelength is approximately 1 millimeter. Okay. These are easy
Hmm.
numbers to remember. So 3 Kelvin, 1 millimeter. Anyway, approximate's good enough. Yeah.
3 Kelvin.
hmm
Wait,
So the
so
so that's basically the average temperature of the whole universe.
it's 3 Kelvin.
Yeah. But of course, there's gonna be hotter spots like where the sun is, where the stars are, where galaxies are. Those would be hotter spots, definitely.
Okay. So when the universe was smaller,
Uh-huh.
it was higher than 3 Kelvin.
Yeah.
Wait, doesn't
Uh
that connect to black body radiation as well?
kind of. You can think of the whole universe as the perfect black body, the
Yeah.
perfect black body, right?
Oh, in microwave background. Sorry, I've said that wrong.
hmm Yeah,
Wait,
but
what
yeah.
was that 3 Kelvin thing?
Okay. The microwave background this let's start with the 1 millimeter thing. Okay, the 1 millimeter wavelength of the microwave background radiation corresponds to a black body temperature for the universe of 3 Kelvin. So again,
Oh, so that's the temperature of the universe,
mhm,
right? Yeah. Okay. Okay.
again, you have to take into account that that's the average temperature of the universe right now. Okay,
Mhm.
what does that mean though? Even though we have a lot of hot spots in stars and galaxies, that basically means the temperature of the universe is way below 3 Kelvin in the spaces between.
Mhm.
Okay. Is there anything else I'd like to add here? Oh yeah, you were saying earlier. So that means in the early universe, like maybe like after the Big Bang, you may be wondering how hot the universe was. Millions
Mhm.
of millions of degrees. It
Mhm.
doesn't
Yeah.
matter anymore whether you're talking Fahrenheit, Kelvin, or Celsius. In fact, it's not millions, it's billions. It's in the billions.
Mhm.
So it doesn't matter what scale you're talking about now, right? Okay. Yeah. So
Hmm.
um, here's the thing though. This is SL, so you don't really need to know this. But in HL, this kind of corresponds to how we know how the universe evolved. The temperatures, cor- higher temperatures basically corresponded to high energies, and that told us how the universe behaved way before, at the very beginning. So all you need to know
Hmm.
now is this, okay? The cosmic microwave background radiation. Okay, all right.
Hmm.
So we're done with this problem. So tomorrow we'll meet again tomorrow, right? We'll do. Which paper have you done again in school? 22? Was it 2022?
22, 23.
Okay, so we'll do a 2021 paper tomorrow for this. Okay.
Okay,
All right. So we'll end here today, CJ. So any questions before we end?
no question.
No questions. All right. So I'll see you then. I'll see you tomorrow, and yeah, have a good evening.
Thank you. You too.
All right. See ya.
See
Okay. So that's the end of the lesson. So on the stream, uh, yeah, so there we go. So that's the end of the stream, the lesson there. So hopefully you learned something. Again, just because we're doing IB right now doesn't mean you cannot use this for other qualifications, like any national curriculum you may be doing, or the SATs maybe, or maybe if you're doing AP Physics in high school, or if you're doing what's this? If you're doing any UK curriculum based stuff like IGCSE, A levels, GCSEs, O levels, that sort of stuff. Again, physics by itself, it doesn't really have anything to do with any particular curriculum. Okay, so I hope you still learn from this, whatever you're doing. So with that, we'll end tonight's stream. Well, tonight for me. But before that, again, I'd like to ask you all to like, share, and subscribe to the channels. So they're all here. And of course, you can go to freakyphysics.xyz for more stuff. Okay, so with that, again, I bid you all a good day, good morning, good afternoon, good evening, good night, wherever you are in the world. And stay freaky, everyone. Bye bye now.